All right, everyone. Welcome back to the second session of our Intro2Astro workshop this summer. I hope everyone had a good weekend, and we are all excited to see all of you here again. Today, we'll talk about various Python packages as well as making plots in Python. And we will discuss last week's reading assignment, the Exoplanet review paper by Dr. Lee. Finally, we will hear from Tim about his life story of how he ended up working as an exoplanet astronomer. Let me remind everyone to use the live chat window on YouTube to ask any questions you may have. Another point I will make is that we understand the lectures contain a lot of information, perhaps more information than anyone can absorb within 1 hour. Again, our aim here is to provide a quick overview of the topics in discussion and to show you where to look for further information. So please use the recorded video and the assignment to consolidate your understanding. If you have further questions, feel free to make a post on piazza.com, and we'll try our best at answering those questions. All right, without further ado, let me hand it off to our first speaker today, Shubh. Shubh, would you please also introduce yourself briefly since you were not here last week?
Yeah, sure, thanks for that. Could you hear me all right?
Yeah, go ahead.
So hi everyone, I'm Shubh, I use he, him pronouns. I graduated from Caltech with my bachelor's degree last week, and I'm going to be a graduate student at the University of Pennsylvania this fall. I'm really excited to be here. I've mostly done research in cosmology, instrumentation in cosmology, but I've also done some exoplanets work. I'm not sure what yet I'm doing in grad school. But yeah. So for my talk today, I'm going to be talking about some Python packages. And we'll be trying to just give a brief introduction to these 4 packages called Numpy, Pandas, Scipy, and Astropy. This is not meant in any way to be a very thorough description because these packages are too extensive to talk about. So extensive that even after, say, like 4 years of using them, I still learn new things every day. And these notes and these slides are derived from previous year's notes and materials from similar workshops that will be available later on, and you can also check out on past year's notebooks. So the first thing, first of all, we'll be talking about these 4 packages, Numpy, Pandas, Scipy, and Astropy. The specific slides were made using these particular versions of the 4. If you ever need to take a look back and just make sure that you have the same version and why things might differ between different versions or something like that. First thing I wanted to mention with anything Python is how to get help. Help is a built-in Python function which is really helpful because if, say, you do not even have internet access to look up documentation for a particular function or for a particular package, that's sort of inbuilt into Python, so you can use this help function. So if you didn't know what a print statement does, which essentially prints whatever value you give it onto your screen, you can run help print and it will give you this sort of documentation, and it will tell you that it's a built-in function and this is how you use the function. So we'll be using sort of this built-in documentation to look at these packages. So the first one we have is Numpy. Just help NP, because I imported Numpy as NP. Just gives you an idea of what Numpy is. So Numpy's documentation is available online at various places, but essentially, Numpy is a powerful numeric library that is fundamental to doing any sort of computation in Python. These are the 2 web pages that you usually associate with Numpy, which has all the information you would need on the various applications for Numpy. And this sort of picture is available on this website, which just shows you the kind of breadth that Numpy has been used for in the past. So applications go from something like quantum computing to signal processing to astronomy, which we're going to be looking to focus on. And all of these links are different packages that we'll build using Numpy or highly based on Numpy. And we'll be talking about some of these, including Pandas, Scipy, and Astropy. So what's the idea of NumPy? NumPy is essentially a way for you to store information. So I'm going to be comparing that to lists in Pythons or arrays in any other programming language. The idea being that if you had some series of information, you can store it in a form of Python list where you give all of your values separated by commas and put them in brackets. It's a pretty straightforward kind of data structure that you use a lot in Python. NumPy is similar to that. NumPy is also data structure, but it gives you other flexibilities. So I'm going to try and compare them to lists. So you can define these sorts of like single-dimensional, one-dimensional lists, or these 2D lists, which essentially has 2 rows and 2 columns. Like this, you can. The way to initialize NumPy arrays is you use a function called np.array or numpy.array, and you pass in the same information as you do with some information about what the structure of the list is. So here you have array that has 1 row and 4 columns, and here you have an array that has 2 rows and 2 columns. The cool thing about NumPy is how it operates with mathematical operations. So if you were to multiply a list by some scalar, by say the number 3, it essentially just takes the list. So L1 here was 1, 2, 3, 4, and it essentially multiplied or duplicated that list 3 times and made you a list that is a combination of those 3 duplications. So it repeated these numbers 1, 2, 3, 4 3 times because we multiplied it by 3, and dividing a list doesn't really make sense because Python does not know how to divide these 4 elements into 3 or something like that. If you did divide it by 4, that would also not work just because it's not supported in Python. NumPy is, on the other hand, is built to do numerical things. So when you say some array multiplied by 3, instead of duplicating that array 3 times and giving you a new array, it simply multiplies every element in that array by 3. So in the first case, we had something like 1, 2, 3, 4. So now you have the multiplication table for 3. In this case, you had, I think, 10, 20, something like that. So that's just divided by 3. All of those. And you can see that it maintained the same sort of structure. How indexing or slicing or iterating over these different data structures work. NumPy arrays are very similar to lists in that you can use a for loop over them to iterate over the different values, and this sort of prints all of the values in both the list and the array very similarly. The indices for NumPy array is also very similar. So if you have an array that's 1, 2, 3, 4, then the first element of one element is at index 0 because in Python we have indexes that start with 0. So the way to get it would be you write something like A1 square bracket 0 would give you 1. The cool thing about NumPy arrays is though that you can do various kinds of different slices with it. Some of these you can also still do with lists, but here are some examples of things you can do. So if you remember, A1 was 1, 2, 3, 4. So say if you wanted the elements between 1 and 3 indices, so this is 0, 1, 2, 3. So if you wanted the elements 1 and 2, so between 1 and 3, you can do something like this. That will give you the second and the third element. And these are just other examples of slices that you can do. So this gives you all the elements before the third element. This gives you all the elements after after the first element, and so on. The cool thing, though, is that you can also do the same thing, but for multi-dimensional arrays, which is something you cannot do for lists. So if you had an array that's 2 cross 2, like here, you can do something like A2 1, 1. So 1, 1 is the second element in the second row because indexing starts at 0, so it can give you this 160 element. And similarly, you can do different slices by using a comma here to represent. So the first slice will decide your row numbers, and the second slice will decide your column numbers. And these are examples that showcase that sort of feature. Other things that you should think and know about is that you would need to think when you would need to consider when you're using NumPy arrays is that indexing does not always need to be just various indices or numbers. It can also be conditions, which is a really powerful tool that allows NumPy to be very efficient at doing different things. For example, if you remember, A1 was 1, 2, 3, 4. Say I only want the elements in this array that are greater than 2. So I can give it some sort of condition. A1 greater than 2 essentially operates this greater than 2 condition on all of the elements. And then if you pass this A1 greater than 2 as an index to A1 itself, it will just pick up the elements that are greater than 2. So this is sort of like an easy way to go through the entire list and only select elements that satisfy a certain condition. The other thing to keep in mind is just setting one variable equal to other doesn't make a new copy of a NumPy array. So if I say something like A is equal to 5, and then if I say P is equal to A, if I change A, then B doesn't change because these are two different variables. But the way arrays or even lists work is that they don't store the address of your data structure in them instead of the actual values. So when you say something like, I will copy A1 as into this variable by just setting A1, a copy is equal to A1. And you can see here that these two get copied. But then if I change the copy, it didn't just change the value in A1 copy, it also changed the value in the original array. So that's something you should keep in mind while dealing with arrays or lists. It's sort of similar. So the way to get around this is use this function called .copy. So if you say A1.copy, instead of just setting it next to A1, then you can do the thing. So here we changed A1 copy, but A1 didn't change because it's actually a full copy and not just pointing to the same location in the memory. With that very quick intro, let me move on to something else called Pandas. So Pandas are really cute animals, and this picture was in last year's notes, which I think we should look at. Moving on, Pandas is another way to store data. Data is stored in rows and columns again. But the idea here is that instead of using numerical indices for different columns, you can actually use any Python objects, and it's usually the Python objects use are strings. You can different columns, just like in an Excel sheet, and you have different columns with different headers. For example, I would show you a tabular example in a couple of slides, but one example of Pandas object is some sort of series which you can construct like this using pd.series that constructs a data object, a linear data object with different indices and different values. This is more similar to a list, but if you were to think about other ways to construct 2D objects, so say you have some information like you have names, birth counts, and percentage of births, different values, but all of these values, like the first and next, relate to each other, and you want to form a table. The one thing you could do is you can construct a dictionary, which is essentially a sort of collection of lists that contains itself like this. But in this case, these different objects are still independent of each other and not arranged in a 2D fashion. So to convert this into data frame, which is the core kind of data structure that is used in Pandas, you can use something called pd.dataframe that converts this dictionary into a data frame, and that gives you this sort of tabular structure. Here you can see that different columns have different strings or different words as the headers, and you can call different parts of this table using these references instead of just numbers. So for example, I constructed this data frame which has this one sample column, and you can add you can refer to that column by just doing something like tf samples. Here the index is not a number but rather a word, and then you can add in more columns to your data frame by doing something along the lines of just setting a new column or a new reference here to some other value. And you can do computations with all of these values, very similar to how you would do computations with Numpy arrays, because when you say something like +1 or divided by 1, it doesn't just do some sort of list application. It goes in and applies that sort of function to every value in your column. So here you can see that say 2 got 2 had itself increased by 1 to become 3 here. It's squared to get this value in this column here. You can also save data frames in as a CSV file, which is a way to just store data, and you can read back data frames from the same file. So this is like an easy way to keep your data saved between files or between different ones. And these are just like other things you can do with data frames. So data frame.columns give you the list of all the columns. Data frame.head gives you just the top 4 or top 5 or whatever number you give here. Column rows in your data, and similarly data frame.tails gives you the bottom n rows in your data. So there's a lot you can do. There's a lot of functionality already built in that we can definitely not cover. For example, there's also sort values, where you can sort by a particular column. And it also supports this kind of functionality that I talked about with Numpy, where indexes could also be some set of conditions, and then it only selects the rows with those conditions. So the question is, there are 2 different ways to store data. Which one you should know? So Numpy is designed to be more memory efficient and more like a faster way to do computations. But it can only store data values with one sort of kind of data, whereas here you saw before that Pandas was able to store things like names or things like percentages or integers. So it's more flexible and it's great for heterogeneous data. So if you have data from different instruments or different kinds of data points where you have, say, some information about location or some information about name or reference, then Pandas is a more flexible way to do that. But if you have large amounts of data, of one kind of data where you have to do complex computations, then you might want to use Numpy because it's faster. In most cases, you end up interconverting between them. Pandas could be a good way to store data, but then you import it and then you convert it into Numpy. It's sort of flexible like that, but that's sort of the kind of application. I'm running out of time, but I quickly want to touch on 2 even more expansive packages, Scipy and Astropy. So Scipy sort of stands for, I had to guess, scientific pi or something, science pi. And Astropy is for astronomy purposes. Scipy, as you can see, is scientific computing, just including these for completeness and where you can find documentation. Astropy is intended to be tools that you need for doing astronomy or cosmology or astrophysics research. Idea here is that these packages have a lot of functionality. So the core idea is when you're doing something new or building something new, you don't need to reinvent the wheel. If you want to do linear algebra, you should go ahead and import Scipy.linear algebra or linalg. Or if you want to do statistics, you should import something like Astropy. You shouldn't spend a lot of time just building something that's already available for you. These are very extensive, so people usually need to only import specific sub-packages. So there are several sub-packages. And so did have the list of a few of those. So Scipy has all of these different sub-packages, which one of them is designed for signal processing, one of them is just for linear algebra, one of them is for stats. So you would import these and then use the functions inside them to do whatever you need to. Similarly, Astropy has all of this, which I'm not going to go into, but these tutorials are available online on the links in the slides, so you should take a look at them on your own time. A couple of them that I wanted to cover, the next 4 minutes, I guess, is Scipy has something called Scipy.optimize.curve, which allows you to do curve fitting. The idea here being that you have some data and an idea of how certain values in that data depend on one another. How best can you estimate the exact dependence? Curve fitting is something that's regularly used in astronomy, so it's a nice thing to have built in. I'm not having to go into. So the idea here would be that you have some data, say some X data, and Y data is directly dependent on it. In this case, it's just 5 times that data. And you have a guess for that dependence. You know that it's somehow dependent just like that it's X times some guess factor. In that case, you can, if you have this data already from some method, you can try doing curve fit on it, and it will be able to estimate that without any knowledge of this factor 5. It was able to estimate that the factor was 5 by using some sort of methods that are built into it. Even if you had like a really bad guess for, not a really bad guess, but a worse guess for how this data depends on each other, say you mistakenly thought that there should be like plus some other factor, it still is able to extract back your dependencies pretty easily by making the other factor to be close to 0. So it's very powerful in being able to extract back any knowledge that you can from your data, given that you have some assumptions about how they should be behaving. Other things that, say, Astropy is really useful for is something that I use constantly. It's called Astropy, excuse me, Astropy constants or Astropy units. So constants saves in itself like a lot of these constants that you use regularly in astronomy, like Planck's constant or like speed of light or something like that. So here I'm able to compute the gravity at Earth by using just constants that are already pre-saved in Astropy. So you don't have to like type them all up. And Astropy also manages your units for you. So you can even convert from one. So here, as you can see, you were able to get a value for the gravity in some specific units, and you can convert between these units by using Astropy.units, which is really powerful. The last thing I wanted to quickly mention is what FITS files are. So FITS files are very commonly used in astronomy to save data. It's sort of like one of the few standards that are left in astronomy. So FITS saves images, and it can do various things, but it's usually used to save 2D images. And here's just some like brief example of how you can use astropy.io to open FITS files, and how there's can be like information saved in those FITS files as well as like an actual image. This picture here is actually very scientifically interesting because this is the first ever picture of a directly imaged exoplanet. So you can see a star in the middle here, and this sort of like brighter blob is a exoplanetary companion that was discovered around the star by using direct images. This is the first picture of an exoplanetary companion that we have. So yeah, with that, that's all. It was probably longer than I was expecting, but we were discussing about, so I didn't feel bad. So.
Excellent presentation. Thank you so much, Shubh. Before we move on to the next speaker, let me take some time to reformat the streaming, which we realize the size is not appropriate. Let's see. Just give me 1 minute. Right, should be good enough. All right, thank you, Shubh. Our next speaker is Hrishabh, who will tell us how to make plots within Python. The floor is yours, Hrishabh.
Yeah, hi. Can you confirm if I am audible properly?
Yeah, you're audible.
Okay. Yeah, I hope you all can see my screen, and I will get started. So yeah, good evening everyone. I'm Srivastava. To start with a little bit about me. So I am a 4th year undergrad from Indian Institute of Technology, Madras. And right now I am in UBC Vancouver working in finding galactic redshifts. So let's start this module of plotting in Python. Before we get into how to make plots in Python and how to like do all that stuff, let's first make sure why are we learning this. I mean, we just covered 4 modules in Python, so why specifically a session for plotting? Because plotting is very important for us, because this is how our human mind works. Whenever we see any sort of data, for us these are just numbers. We don't learn a lot from them, but once we plot them, then only we tend to realize that then only we see some sort of a pattern, and then we can make some predictions or analyze that data or whatever. So yeah, this is the reason why plotting is very important for us. Now, let us continue with Matplotlib. Start with, what exactly is Matplotlib? So Matplotlib is a library in Python which helps us to plot. And yeah, it consists of lots of functions, and it is very flexible. It helps you to make different types of plots to make different sorts of analysis. So yeah, let's get started. And yeah, we will start with installation of Matplotlib. So there are like various commands that you can use for installation of this Matplotlib. So I'm working in a Jupyter notebook, so pip install Matplotlib would work for me. This is a very common command. It should work for like most of you, and if it doesn't, then you can just check out the official website for which the link I have provided here. And like there are various other commands as well which can be used. So yeah, once you install Matplotlib, now you can continue on working on it. Okay, so for working on it, firstly we need to import this library. So here I am importing Matplotlib as MP and matplotlib.pplot as PLT. Okay, one thing to mention about this magic command called %matplotlib inline. What it does is that it helps us to get the output plot in the Jupyter notebook itself. If you're writing a Python code in your own PC in a .py file and then compiling it using some internal compiler, then you will get your plot in a separate window. Now this command helps us to get this very same plot in the same file, which is like yeah, a lot better for us. Now I have imported the file. Firstly, I imported Matplotlib as MP and then matplotlib.pplot as PLT. So this pplot module of Matplotlib will be used directly for plotting, and yeah, we'll see what these two are used for. Let's get started with firstly with a very simple plot. I'm importing our maths as empty and Numpy as NP. We just saw what all Numpy can do. So Numpy is very important for our work. And for a simple plot, okay, there's one more thing that I want to mention. In Matplotlib, we don't give an input directly functions, as in we don't give fx is equal to x square or 2x square or whatever. We have same size. So for that, we are creating one x array which will form the x-axis here. And secondly, we are creating this we are creating this y array. So we are actually creating two arrays here just to like see how two plots work. This will create an x array from -5 to 5 having 100 points, 100 data points, and then y1 will have like a cube of all those points. Like for example, if the first element in x1 is -5, then first element in y1 would be -125, and the first element in y2 would be 25. So yeah, let's see what happens next. Okay, before proceeding ahead, yeah, I guess Shubh covered this part, the use of help and dir, wherein you can, just look for how a particular, there are lots and lots of functions and lots of libraries in Python. So just to read about how each and every function works, what are the parameters and how to use it, you can use this help command. Yeah, I'll just, go ahead. And yeah, here what am I doing? I'm fixing the font that I'm going to use for my plots as sans serif, and I'm putting size to 20. And now this is how I make a plot. Let's go like one by one through all these lines. So firstly, I have like fixed the size of the plot that I want, because the size of the plot is very important. It just, if plot's too small, then we might miss out on certain stuff, and if plot's too big, it does not look good. So yeah, size is important. And this would be the first line. This is like the most important line while plotting. plt.plot x1 y1 r dash and label. So let's go through it one by one. So the first thing, x1 is my array which would form my x coordinate. The second one would form the y coordinate, And the third one, this R minus, what this would do is that R refers to red. So this would, the plot, whatever I'm plotting, it will come in red, and the the dash, it will give me a line output. So as you can see in this plot here, we have a line plot which is red in color. And now I am labeling this plot as y is equal to x cube. And you might be wondering why are you seeing these dollar signs here. This is written in a format called as LaTeX, about which you will learn in your upcoming sessions. Similarly, I'm plotting one more plot, which is the Y2 plot, and it is very similar. The only difference is that here I'm using B with a dash, I'm using a dot as well. So look at the type of the line I'm getting in this plot with the dot and dash. And then I'm fixing my X limits from -5 to 5, Y limits from -30 to 30. It's up to you to decide how much limit you want to keep. Then I'm, my X-axis label is X, Y-axis label is Y is equal to f of X. It is, while making scientific plots, it's like very important to have perfect labels. And then the title of my plot, I'm putting this simple plot, and PLD.grade visible is equal to 2. So usually your plot, it does not have a grade. By default, it is set as false, but it's at times it's good to have a grade. If you want to locate points, it is very helpful. That's why I have kept grade as true. And then PLD.legend. PLD.legend would help me give this output, as in I have labeled my plots, but PLD.legend command would show these labels in the final plot, and then PLD.show. So this is the plot that I have. Now I have opened this PLD.plot help file just to let you know all the combinations that we have for this, like R dash, B dash and dot and everything, because this will help you know what all features can be used. So yeah, if you see, you'll just get what PLT.plot function x comma y x comma b, or meaning of everything, whatever I just said. And then if you scroll a bit lower, you will see, this description of each and every characters that are there. Dot will give you point marker, which will be a dotted line. Then comma will give you pixel marker, and different kinds of plots like. And then line types, I used a dot and a dash, which is the dash dot line style. And then the various colors, blue, green, red, cyan, magenta, and everything. So like, for example, I can show you, I can change this plot. I can put upper triangle and see, this is how this plot now looks like. So yeah, you can just play with it and you can just see how like each and every lines can look like. And we'll go ahead now. No, this was just a simple plot that we saw. We don't usually plot very simple plots in Python because you have done all these plots before as well in your schools and everything. Now, when you come to real scientific world, all you get are data points and you have to plot that. So one of the most important type of plot that we use is the scatter plot. So firstly, we'll see what a scatter plot is. Then we will move on to see how is it used, like for scientific plots in general. So instead of a line in scatter plot, we plot individual data points. Now here I am defining another array for this point. Now this will go from minus pi to pi. Now empty.py, empty math library. So .py will make Python understand that I am importing the number pi. And again, and my y3 would be sign of whatever array I have in here. And this is how I'm using almost all the commands are very same. Just look at this line. We had plt.plot in that simple plot, and here I have plt.scatter, in which my x-axis has x2 and for y-axis y3, sorry. And I have labeled it as y is equal to sin x, and when I like plot it, everything else is same. This is what I get, the plot of y is equal to sin x. So that's how a typical scatter plot looks like. But again, if you want to plot this type of plot, why do you need a scatter plot? A line plot would look much better, isn't it? Because this is not something that we use scatter plot in generally for. Now we will see, like in real life, how do we use these scatter plots in real scientific plots. Now, what we will do is that we will get data from a file and we'll try to plot that, because that's what our job is, isn't it? Now, So I'm taking my data from a file temperatures underscore ghana.txt, and yeah, this file will be made available to you later on, through which you can try. And in this file, we have like one column of dates, which mentions like all the years and temperature, average temperature in that year. So I have made two Numpy arrays here. Date will have all the dates and temperature will have temperatures in those dates. And I'm loading it using load txt function of Numpy. And then, yeah, all the commands are pretty familiar that we used before. And this is what I'm doing, pl.scatter date, comma, temperature. Now see, this is what I got. Now, I mean, again, this does not, make lots of sense. It just looks like someone has thrown a bunch of points in a particular plot. So yeah, so this is just an example to show. And yeah, even to me, it does not make lots of sense, but there are some things that you can see. Now, when you look at some regions of this plot, you can notice that there are certain regions, like I hope you can see my mouse. So there are certain regions like this one where the density of points, the number of points are very less. While there are some regions like, let's say in the almost in the center one, the number of plots are like very high. So, I mean, this, through this you can understand that this is the, region wherein temperature usually is. So let's say if this were a plot of let's say mass and radius of an exoplanet, then you can sort of understand that exoplanets having like radius in a particular range would have mass in this particular range. So this is how it helps us. But there's something more. Now you can see here that all these dots, like, okay, these are supposed to be points and points are dimensionless, but obviously we can't see something which is dimensionless. So when we draw it physically, we tend to, give our points some width. Now what happens is that when these points are like too close, they tend to, get merged into one another, and it does not make like things very clear, because there are some regions in which I can realize that there are like multiple points, but I can't understand how many points there are. So our scatter function, it provides another parameter called as the alpha parameter, which gives us the transparency to this plot, and which helps us a lot in this regard. So I have using the very same commands, just that I am including this alpha parameter here and putting it to 0.6. I guess we can vary it from 0 to 1. And this is how the plot changes in this case. Now, since it is becoming a little bit transparent, I mean, we can start, sort of realizing stuff that, okay, this region looks a bit, dark as compared to this region. So, I mean, there must be more number of points there. So yeah, this is what it is all about. Now, I just want to mention that, okay, there are things are not very clear in this particular plot, because this is temperature with year. But like the example that I gave, let's say mass and radius of an exoplanet, if you plot that, you might see a bunch of, a bunch of points in a particular area, through which if you like draw a line or a particular curve, you are able to cover most of these points. So if you do that, you have sort of, realized a relation between the mass and the radius of all the exoplanets. So that's how scatter plot helps us. If we like fit them properly, then we tend to get a relation through which, in future, if someone gives me a radius of an exoplanet, I can give them the mass. So yeah, that's how it works. I mean, this is called as regression, which is using machine learning. Yeah, and you're gonna do lots of these things.
Hrishabh, we are losing your audio.
Oh,
You're not speaking.
just a minute.
Yeah, we can hear you now.
Oh, okay, all right. I'm audible, right?
Yes.
I'm audible, right?
Yes.
Oh, okay. Oh. Yeah. So moving on to the error bars. Now, what exactly are error bars? We don't get accurate data points in scientific plots. What we get is that we get like in all the data points that we get, there are certain ranges of error in that. for example, about mass of an exoplanet, I can't say that this is the mass of this particular exoplanet. I'll say this is the mass of this particular exoplanet with uncertainty of like this much amount. So for that, when we make plots, it is also important to, include those errors in our plots. So for that reason, we have one more function in
So Hrishabh, we are losing you again.
Oh no.
Okay, you're back.
Yeah. Oh my God. I'm really sorry for this.
Maybe try turning off your video.
Yeah, sure. Just a minute. Yeah. Okay. So yeah, continuing with error bar. So I have created this error just to show you how it works. In general, you will be given error for each and every measurements that you can plot. Now, yeah, let's move ahead to the next type of plot, which is histogram. Again, which is another type of plot like that is very important. Now, histograms, histograms are sort of the plots that gives you, the number of, let's say we are plotting radius of exoplanets. So histogram will have like radius in its x-axis and the number of exoplanets that has that particular radius in its y-axis. And then it will give you how many exoplanets have radius in this particular range or something. Now, this is a very important type of plot because this has helped us give lots of information which we couldn't have gotten using, maybe usual plots. Like for example, there's a term called as Fulton gap. Now, I'll just urge you guys to read about it, what exactly it is and how we got it using histogram. And yeah, this is a very straightforward way to plot and we have a direct hist function for that. And okay, we are running out of time. I'll just, you can just read about everything that has been explained in here. And yeah, before ending, I would like to mention this important part about saving plots. Because saving plots is a very important feature because you don't only plot to keep it in a Jupyter notebook or in your Python file. You make plots to show them in the paper that you want to publish or show them in your project. So it's important to save whatever plots you have made as well. For that, Matplotlib, it provides a direct function plt.savefig that you can use, and you can save plots in various formats. Now you can you can read about all these formats, and yeah. So yeah, that's it. So in the end, I would just like to mention that keep playing around with Matplotlib and make plots, and you never know what you might get from a database. Someone might have missed something that you might end up plotting and finding something exciting. And you can just do all these exercises and extended exercise if you're interested in it, and just and if you have doubts, you can put them on Piazza. Okay, yeah, thank you.
Thank you so much.
And I'm really sorry for the interruption in between.
Don't worry about it. Some very nice plots you have there. Thanks so much. All right, let's move on to our next speaker, Priya. Will tell us about the exoplanet review paper.
Yeah, thanks, Faye. So I hope you all can see the presentation fine.
Yeah, okay, go ahead.
Yeah, okay, great. So thanks. So hello everyone, I'm Priya Hasan. I'm a professor in physics and astronomy at the Maulana Azad National Urdu University, which is located in Hyderabad in India. And today I'll be talking to you about this review paper, which is on exoplanets, the past, present, and future. So by definition, an exoplanet or an extrasolar planet is a planet outside our solar system. So the first step is to look for exoplanets. How do we actually look for them? And that's what's basically described in this paper. The paper basically describes different techniques or methods which are used to detect exoplanets, and that's what I'll talk about. So first of all, the question is, why do we look for exoplanets? And this would be, I'm just putting this in just as an inspiration quote to everyone. This is the famous quote given by Carl Sagan in the movie and the book Contact, where he says that the universe is a pretty big place, and if it's just us, it seems like an awful waste of space. So that would be, I'd say, the driver in actually looking for exoplanets, and why are we so convinced that we should have exoplanets as well as habitable universes which we need to find. So what are the different planet detection methods? There are many different planet detection methods. It's an old plot, this is 2012, but this very well describes the different methods which are used, from dynamical effects, timing techniques, microlensing, photometry, miscellaneous. I'll be talking about each of them in more detail, but obviously there's a difference in the kind of sample or the kind of exoplanets you detect using different methods. So briefly, the detection techniques are, there's the popular technique of radial velocity. There is one which is using transit photometry. There is microlensing, and there's direct imaging. These are the 4 techniques I will talk about today, which are also discussed in the paper. Now, if you actually see till the year 2020, you see that there has been a distribution of the techniques which had been used. Earlier, it was essentially a lot of radial velocity, because that was the method that was available. And then by the time Kepler got launched, that was a satellite mission, a space telescope, which is basically looking for transits. You can see that now the contribution from transits with Kepler and then followed by TESS, you now have a larger contribution coming in using transit method compared to radial velocity. But still, essentially, radial velocity and transit are the 2 most important methods. You also have other methods like microlensing, imaging, but they are obviously much lesser in contribution compared to the other ones. So let's first of all start off with the radial velocity technique. The radial velocity technique is essentially using the effects of gravity. So for example, if you have a star and a planet, they are both going around their common center of mass, which you can see over here. And because of that, you basically have a wobble in the star's position, which also means a wobble in the star's velocity. So if you were observing the spectrum from the star, the spectrum would be redshifted, and would be redshifted while it's going away from us, blue shifted while it's coming towards us. And based on that, you can actually detect the presence of the planet. So another nice graphic showing you that if you were to actually look at the spectral lines, here you can see the spectral lines. The dotted lines are the lab values for the spectral lines. And you can clearly see that there is what is called a red shift, and there's a blue shift in the position of the spectral lines as the star is going around its common center of mass. So in this case, you are not detecting the planet is too small. You are just detecting the wobble or the change in the velocity of the star as it's going around this common center of mass. And this shift is basically what is being measured. Now, like I mentioned, this shift is basically the Doppler shift, and obviously it depends upon the ratio of the star and the planet, because that will tell you how do you see the actual wobble. If you were to see it in case of Jupiter, for example, it barely gives a variation of 13 meters per second. Earth, if you were to observe it, it would give you a variation of only 0.1 meters per second. And therefore, it obviously is very dependent on the sensitivity of your detector. So on the ESO 3.6 meter telescope, the HARPS instrument has a measurement limit of about 1 meter per second. So you would easily be able to detect a Jupiter-like planet using HARPS. And this is exactly what is used by the Geneva team when they measured radial velocities using HARPS. And I'll come into a minute into the Geneva team. But essentially, the problem in the radial velocity technique is that you are only going to see the component of velocity which is along your line of sight, right? And therefore, you are only seeing that projection. And there was a question also on Piazza on why is it the lower limit? That's because you are only seeing the component which is in your line of sight. And supposing if so it's essentially an M Sinai kind of component. So supposing if the velocity was only in the plane of sky and nothing in the line of sight, you would not see any line of sight because your Sinai would be 0. You would not see the component. And essentially, because you're only seeing this component, the formula is essentially this, and you're only seeing that component, so that would limit the mass that you would be detecting. So that's the lower limit. Now, a bit of history, the first exosolar planets were basically found using pulsar timings, which is now not so popular, but essentially that was used earlier. And the first exoplanet around solar-like stars was detected by Mayo and Quillitz in 1995, for which they got the Nobel Prize. And this was 51 Peg, the exoplanet, which was detected using radial velocity technique. So that's exactly what Didier and Perlitz got the Nobel Prize in 2019 for the first detection of the exoplanet around a sun-like star. And this is using the radial velocity technique. Here you have both of them. And you can actually, essentially what you're doing is you are measuring the delta lambda by lambda, which gives you the V by C. And like I mentioned earlier, the V is the projection in the line of sight. So that is dependent on the resolution or of the spectroscopic instrument which you are using. Now, the future telescopes, for example, the extremely large telescope will actually, the Codex instrument will give us a superb capability of 2 centimeters per second, which would mean that you would obviously detect even Earth-like planets using that kind of an instrument. But this will come with the European ELT. The present instruments, like I mentioned, give you about a 1 meter per second, thing like that, and that's our present capability. The disadvantages of radial velocity is that you could also have such a shift coming because of various other effects. For example, you would have false signals coming because of multi-planet, multi-star systems. If that could also give you the wobble. There could be stellar activity or magnetic fields which could actually give you this kind of a wobble. And therefore, what's very important, which was even in the work done by the Geneva group, was actually calculating the effect which you could get from all these effects, multi-planet, multi-stellar, stellar activity, etc., to rule out all those false positives, and then finally attribute it to the presence of your, of the planet that could give you the system. So the other popular method which is used is the transit method, which is a very simple method in the sense that if you have the planet coming in front of the sun, you will have a dip in the brightness of the light coming from the star, and that is called the transit method. But the transit method, like you can see, is that it obviously depends upon the ratio of the squares of the radii of the two, the planet as well as the star. So for example, if you were to take it for the Sun-Earth system, you take the ratio of the radius of the sun to the radius of the star, you would see that the ratio is about 10 power 4. And therefore, the kind of precision in the photometry which you would require would be less than 1%, right? You need, because this dip over here is exaggerated, you can see a large dip, but essentially the dip is something very small. So for example, if you had 1,000 light bulbs, if one of the light bulbs was switched off, you should be able to detect that. And that is the kind of precision you will require in your photometry if you want to detect it, right? So that is the problem with the effect if you're using transit photometry. But for example, we'll come to that in a bit. If you have your photometry from space, then you can look for that kind of a precision, and that's exactly what Kepler and TESS achieved in their data, right? Now, the other method which is used is the micro-lensing method. Essentially, what that means is that if you have a lens star orbited by a planet, what you would have is, because of the gravitational lensing effect, you will have multiple images being formed. And if you have multiple images being formed, you will have a variation in the brightness of the star. And that is the exactly variation which you are trying to look for. But obviously, getting this kind of a variation for this perfect alignment to take place so that you can get this kind of an effect was actually calculated by Brzezinski, which is a chance of 1 in a million. So it's a very, it has a very low probability. It's a low probability event, as well as it will not get repeated. And therefore, it's a little bit of a, it's a difficult event to find. It has been used by various surveys, the Macho, Eros, Ogle-Moore survey, which actually looks for it. But it can detect mass and orbital distance without ambiguity, can detect very low mass exoplanets, and it can also be used for looking for exoplanets in other galaxies, for example, in M31. The other technique which is used is the direct imaging technique, but it's obviously very difficult because the star is going to be much, much brighter than the planet, and therefore, because of the contrast, which could be even a factor of 10 power 9, a billion times, it would be very difficult to actually detect it. And for example, Jupiter's sun at 5 parsecs, the angular separation is less than bar arc seconds. It's very difficult to actually detect it. So what is the way of doing it? The simple way of managing this thing is, for example, if you want to look at the sun, right, the corona of the sun, the typical method used is to use a coronagraph. That is, you you block out the light coming from the star. And that's exactly what is done, is you actually, if you want to look at the star and you want to see the variation in the brightness, this is the planet coming in front, you close or you cover the star so that you can see the brightness coming from the planet. And that's exactly what is done by various instruments, which are detect imaging instruments, for example, on the Keck telescope, or you can see an example here of a VLT image of a hot young planet around a brown dwarf star, or even the HST, the Hubble Space Telescope, uses a coronagraph to actually look for planets around the star Fomalhaut. So these are techniques which are being used. They are a little complicated, but they are effective in actually getting that. So you can see that, for example, for this star, you can actually detect the three planets which are there, and you can, they've been done. Beta Pictoris is another planet which is being this thing, which again could be used using the VLT, the Very Large Telescope. Could actually use, put a coronagraph to actually then detect the planet. Effective planet hunters are space-based telescopes. These are using the transit method. Like I mentioned it earlier, you need very high precision. And therefore, Kepler telescope was dedicated just looking for planets. It was launched in 2009. And it basically looked for, it's a Schmidt-type telescope with a 0.95 meter aperture, with a 1.4 meter telescope, looking for these things. So it basically looks at a certain part of the sky and looks for variations in the brightness of stars. There have been various exoplanet missions. In a way, Hubble and Spitzer also have been used for looking for exoplanets, but Kepler and TESS are dedicated missions specifically meant for exoplanets. The James Webb Telescope, as well as Plato, is also going to look for exoplanets other than the other programs which they actually have. So the Kepler mission basically looks at a particular field of view of the sky and actually looks for variations around it. Kepler data is freely available, so you can actually do projects looking for Kepler data and looking for light curve analysis of stars and characterizing the exoplanets using Kepler data. This can already be done by you. There was a problem with Kepler, which actually happened because of the reaction wheels in 2013, but there was a solution got to this, and the following mission was called the K2 mission. There was a question in K2 in Piazza on the K2 mission. So basically, the effective wheels now on Kepler are only 2 reaction wheels, and therefore the third wheel was actually, the precision was used by solar pressure, due to which there was a slight change in the kind of the work being done using Kepler now, which is now called the K2 mission, because the third reaction wheel is being replaced by the light pressure which we're getting from the sun, and in that way you can actually balance the thing. The idea is you need very high precision alignment also for the spacecraft, which is achieved using the reaction wheels. So you use the 2 reaction wheels as well as the light pressure. I will answer the question in more detail in Piazza, and we can continue the discussion on that. The follow-up to the Kepler mission, which is now not functional, in 2018 it was off. You had the TESS mission, which was launched in 2018, which is a follow-up of the Kepler mission. And even TESS data is freely available. We'll have a session on how can you use TESS data again to look for exoplanets and follow up with that. What we find is that there are various planet types which are detected using different methods. There are gas giants, super-Earths, terrestrial-like planets, as well as Neptune-like planets. And what is done is using various techniques, we try to characterize exoplanets. And so you basically characterize them using various parameters. For example, here it is using the size as well as the orbital period, in which you can characterize different kinds of exoplanets, the hot Jupiters, the cold giants, the rocky planets, etc. You could also characterize them using the radius of the planet as well as the orbital period, using various techniques. And they gave us various information about them. For example, the Jupiter-like planets, the Neptune-like planets, the Earth-like planets. Like I said, it also very sensitive to the kind of methods used to detect them, because some methods are more effective in finding different kinds of planets. Another important thing is you actually would like to see the planet size and compare them with Earth sizes to get it like this. A very important parameter is the radius versus mass, because that gives you an estimate of the density of the planet, which gives you an estimate of the composition of the planet. So if you actually have a handle on the density, you can actually talk about what kind of a planet you are actually looking at, and that's what people try to infer from the data you get from exoplanets. And another important thing is the atmospheric composition. So what is done is called transmission spectroscopy, and Hubble and Spitzer have been used effectively to actually look for the atmospheric composition. And the James Webb Telescope, which will soon be online and be in functional mode, it will also do the atmospheric composition, essentially using targets which are found by Kepler, TESS, and other missions. So then James Webb can actually do targeted surveys of the atmospheric composition of certain shortlisted exoplanets. And another important thing I wanted to point you about is that in the orbital distance also, Kepler has found about 30 exoplanets in habitable zones. We basically look for planets in habitable zones because that's where we'll actually look for life. But there's another important factor that you could also have planetary migration. Planets could actually migrate in and out of the system. So they could be formed at a different location and then they move. And therefore, there's a lot of interesting research being done on how actually planets are formed, at which positions, and then how do they migrate. Because we know that migration has even taken place in our solar system. Jupiter is not exactly where it should have formed. And that's also a very interesting thing to study with planetary studies. As well as there are also more complications to these problems. First of all, looking for multiple systems. For example, if you're seeing a transiting planet and you have a multiple amount of planets for that star, you could actually have different dips corresponding to that. And then there's also a new, very interesting field of actually looking for free floating planets, which is something that is also very interesting, but cannot be, which is more difficult to handle. But that's also an important piece of research. So I'll end with this. And I would say that we have a lot of exciting times ahead with data from Kepler, TESS, and then other data which will come in, which will be using extremely large telescopes, including James Webb, as well as the ELT, the TMT, and the GMT. So we do have very exciting times ahead with more work being done. Thanks a lot.
Thank you so much.
I'll answer questions on Priya, sir. Yeah.
Yeah, thank you so much, Priya, for that really comprehensive review of the entire exoplanet field. Thanks a lot. All right, let's move on to our next speaker and final speaker, Tim. The floor is yours, Tim.
All right, hello everyone. As stated, my name is Dr. Timothy Holt. You heard from me last week where I did a bit of a presentation. Now I'm just going to give you a little bit of a history about myself, a bit about my path to where I am today. It's not exactly a straight one, and as many of you seem to know, that you seem to take comfort from that it's not a direct path from, you go to high school, then you go to undergraduate, you go from undergraduate to grad school, you get the PhD. That was definitely not my path. I am nearing in my late 30s and I only just got my PhD. So it's definitely been a bit of a long journey. To start with, I'm actually from a very international background. If you didn't guess the accent, I am Australian. I grew up, though, in the diplomatic services. So my father worked for the Australian government and I lived overseas for most of my early life. I did a couple of years in Spain, a couple of years in Thailand, and eventually graduated in New York City. So from there, I went to a university in Australia called the University of Southern Queensland. It's in the semi-tropical north, basically halfway up the eastern coast of Australia. And I did not study astronomy. My actual first degree was zoology and evolutionary biology. So I got to dig up dinosaurs in Western Queensland for most of my career. I have a published paper on this. It was on my honours degree. It was describing a fossil crocodile from the same area, in Queensland. So Then after my honours degree, I got to thinking about getting a PhD, going on, and I didn't quite get the mark that I wanted in honours, and looked at the job prospects in the paleontology, and they're abysmal. They're actually much worse than astronomy. So I actually went into retail. I've been a retail salesman for almost the majority of my life. I've been sold everything from toys in Toys R Us to mobile phones to computers to I actually spent some time in a place here in the US called Barnes & Noble, which is a bookstore. So I got to sell some stuff in there. And then, so I started selling computers. If you're in Australia, it was at a place called JB Hi-Fi. I then moved from that into thinking, well, it's about time I started thinking of a career in my mid to early, mid-20s by that stage, and decided that was I could either go into a retail management career as a career, and I didn't like that. I didn't like the way that the retail managers are treated, and I didn't see myself in that sort of career. So I actually became a high school science teacher. So while I was at JB Hi-Fi, I was working alongside and getting my high school teaching certificate. So I became a high school science teacher at a Montessori high school, which is a non-traditional set of pedagogy that we teach. For those of you that are interested in that, Montessori does not only just do early childhood, but it actually has a curriculum all the way through university, although it's usually only implemented up to high school level. And so I continued to do that. I, amazingly enough, wanted to teach high school level biology. I have a full degree in it, but I couldn't because I was only had one course in chemistry. So some of my I would have had to have taken one more course in chemistry in order to do that. And despite my wife's love of chemistry, it's just not my thing. So I decided I have a huge love of science fiction. If you notice my background, brownie points if you can pick the game that it's from. It's actually something that I've been playing for over 17 years. Then so she pointed me on to a online astronomy program in Australia that was nested, Swinburne Astronomy Online, which offered a degree program. Basically, you could take one or two courses, or if you took a couple more, you could get a certificate, and then if you took all the way through, you got your master's. So yeah, I decided, oh sure, I take the International Baccalaureate Philosophy of a Lifelong Learner. So I decided, well, okay, I'll take a couple of courses in that and see if I enjoy it. So I took a couple of courses and I found that I absolutely loved astronomy. So I kept going, basically. If the original plan was to finish off the master's and then be certified to be able to teach high school level physics. During that time, I did a couple of project-based courses that really gelled with me. I started to take a technique called cladistics, which is a biological technique which most people wouldn't have heard of, and meld those across to the astronomy program, particularly planetary science. That's where I seem to have landed. That's what I enjoy. I enjoy mainly small solar system bodies like the irregular satellites of Jupiter and Saturn, which ended up being my first paper in astronomy, and the small solar system bodies, so asteroids and Trojans and Kuiper belt objects and the like. So what I've been doing, in the meantime, my wife got a postdoc here in Boulder, Colorado, which is a place that's in the middle of, just on the eastern slope of the Rocky Mountains. We're about converting, I don't know what it is, we're about a mile high here. So the mountains that I can look out my window and see are actually higher than the highest mountains in Australia. So it's kind of cool. And over here we have a place called SWIRI, Southwest Research Institute. So I started going to some colloquiums there. even while I was still doing the master's degree and talking to some of the researchers there, and ended up landing with one of my local PhD supervisors, David Nesvorny. So I did some work. Who's an eminent n-body dynamicist. So what n-body dynamics is basically you put a whole bunch of test particles into a supercomputer, throw in the planets and let it run under Newtonian dynamics and some non-Newtonian dynamics and see what happens to them. And so I got to see during discussions with these people at Swiri, the profession of being a scientist and the profession of being an astronomer. And that was a key deciding factor in me deciding, okay, let's make a career out of this. And I approached my university in Australia, University of Southern Queensland, Professor John T. Horner, and said, look, I'd like to do a PhD, but there's a catch. And the catch is I can't come back to Australia to do it. I will need to do it remotely in the US. And because of my honours degree and the fact that I'm an Australian citizen, I was able to get a stipend and a scholarship to be able to undertake my PhD, and got a desk at Swiri and basically lived there for 5 years. I was just told the other day that the desk at Swiri had been there for I'd been there for 5 years, so all the way through the pandemic, etc. I've been doing my PhD remotely as a mid-30s professional. So and then now it's just I finished up the PhD in October last year, and now I am working, basically doing lecturing at the university remotely, so recording lectures, doing marking, handing out assignments, coordinating via the chat programs and that sort of thing. So that's my story. Hopefully it'll give you some ideas. I tend to be heavily involved in all sorts of really cool extracurricular science fiction stuff. A couple of weekends I'm going to be giving some presentations at the Fan Culture Con down here in Denver, which is a couple of thousand people getting together and talking about science fiction and pop culture and all that sort of stuff. And I always enjoy that, linking that and using that, the links of science fiction and speculative fiction into what we see in science, and using that as a hook to learn more about it. And that's where I am today.
Thank you so much, Tim. Would you mind sharing us with the link to your presentation later? I think some of the participants will be interested in that. Or
the presentation. Well, I don't have an actual presentation. It's just me giving the story. So
okay.
I can give you a link to my website, and that's got a lot on there. So
cool.
Would you like that on the?
We can share with the participant later, like in the description. You can just send it to me, and I'll share it.
Yeah. Okay. So it's pretty simple. It's just timothy.holt.com.
Cool.
Yeah, that's my website. It's got everything on there. It's got a bit about my history, what I'm interested in, some links to all sorts of different things, what I work on. So yeah, if you want to check it out, feel free.
All right. Thank you so much, Tim. And thanks to all of our speakers today. Before we end, let me remind everyone to check out the assignments for this week, our course website, and please post any questions you may have on piazza.com. We'll do our best at answering those questions. Next week, we'll take a look at some real astronomical data from the ESO Gaia mission, and we'll also learn about the nearest exoplanet system, the one around our closest stellar neighbor, Proxima Centauri. All right, take care, everyone. See you here same time next week.